Hi, I'm Callum, and this video serves as a broad overview of my final year project entitled DAB Processing Chain for Passive Radar Applications. The video begins with some context, followed by a brief mention of the theory underpinning the DAB standard. Then, a description of the designed processing chain is given, along with a mention of the validation steps taken. Passive radar is a variant of radar technology in which no dedicated transmitter is required for operation. Instead, such systems use so-called illuminators of opportunity, such as existing radio station broadcasts, for the detection of objects in a scene. In recent years, there has been a growing interest in the use of digitally modulated signals as these illuminators, since they offer a host of benefits in a passive radar context. One such signal is defined by the Digital Audio Broadcasting, or DAB, standard, an increasingly popular mode of digital radio. The aim of this project then was to research, design, and implement a DAB processing chain in MATLAB with the context of passive radar in mind. The DAB standard is built upon two core concepts: coded orthogonal frequency division multiplexing, or COFDM, and differential quadrature phase shift keying, or DQPSK. Essentially, COFDM multiplexes multiple bit streams onto independent subcarriers. These subcarriers are chosen to be orthogonal over the integration period, which means that they can be spaced very closely together in frequency without inter-carrier interference. DQPSK is the means of modulating these subcarrier waves. The phase value of each subcarrier is modulated by pairs of bits to one of four possible angle values, hence the word quadrature. However, instead of the absolute phase values being used here, the difference between consecutive phases is modulated, hence differential QPSK. Many hundreds of COFDM subcarriers make up a single DAB symbol, and an array of consecutive symbols comprises the DAB frame. In the time domain, the DAB frame has three important regions: the null symbol, where all COFDM subcarriers are set to 0 for coarse time synchronization; the phase reference symbol, which is a predefined waveform to be detected for fine time synchronization, as well as to act as a phase reference for the DQPSK demodulation; and finally, the data carrying symbols, the details of which are unnecessary for passive radar contexts. The DAB processing chain was designed in three primary blocks, namely pre-process, demodulate, and remodulate. Each of these blocks in turn contained sub-blocks. The pre-process block was designed to read in a DAB recording from a binary file and output a single DAB frame. Most important in this block was the phase reference symbol detection routine, PRS detect, which used a sliding matched filter to detect the beginning of a frame, thus synchronizing the signal. The demodulate and remodulate blocks were the core of the designed chain. Importantly, these blocks were designed to act in tandem, receiving a noisy DAB frame and outputting a perfectly reconstructed, denoised equivalent of that frame. The DAB demodulation routine begins by splitting the data into COFDM symbols, which then can be demultiplexed into the COFDM carriers via a fast Fourier transform. Thereafter, the carrier's data can be demapped. Since the phase values are differentially modulated, consecutive complex carrier values can simply be divided in order to obtain the phase difference between them. This data is then frequency de-interleaved, which is simply a technique in the DAB standard to mitigate the effects of frequency selective fading by shuffling the indices of the data. After this step, we know that these angles should only take on one of 4 values, and thus we can snap the points to their nearest value, removing the noise from the data. This process uses a hard decision boundary by simply looking at which quadrant the angle is in. A full processing chain might then also include an error correction step. However, these considerations were outside of the scope of this project. The remodulate block is somewhat simpler after considering the demodulate block. Notice that the 4 subblocks here are the inverses of the first 4 subblocks of the demodulate block. For example, previously there was a DQPSK DMAP subblock, and now there is a DQPSK MAP subblock, and so on. As a quick overview then, firstly, the snapped DQPSK values are frequency interleaved, and then mapped back onto CoFDM subcarriers via a differential modulation process. The DAB carriers are then multiplexed into CoFDM symbols, which can then be repacked into a DAB frame. This concludes the process of converting a noisy DAB frame into a denoised, perfectly reconstructed equivalent. It was vitally important to validate the designed processing chain, and 4 sets of tests were performed for this purpose. These were graphical tests, inverse relationship tests, repeated processing tests, and reference data tests. All of these tests passed with a variety of input data, and therefore there was cogent evidence that the designed processing chain was indeed working. In conclusion then, the aim of the project was satisfied. A DAB processing chain was designed in MATLAB and it functioned correctly. Nonetheless, there is certainly more work to be done, and future researchers should look at optimizing the processing chain, including other features such as frequency synchronization, and eventually integrating this chain into an actual passive radar system.